Hey you guys, here we are again, learning online. I know there's better days, but hey, you take a little sleeping in anyway today. So today we're going to work with 3.5, Kinetic Molecular Theory. And this is one of those things where you need to know, but you need to know to be able to reference it instead of like spit it out like steps or whatever. So I'll kind of like direct you in that as we go. Also, another thing, what's real important today is Maxwell-Boltzmann distribution. It's a graph that we're going to look at, and it just doesn't go away, you guys. So you're going to see it a lot in AP, and it's not terrible to interpret, I promise. And finally, we'll just take a peek at the kinetic energy and what's going on in those molecules, especially in gases. So here we go. First off, kinetic molecular theory is basically just telling us about gases in general. So gases consist of particles, and those particles we could say molecules, like water molecules, or individual atoms like argon. Molecules could also be the diatomics, like nitrogen, N2, or oxygen, O2. And they are in continuous random movement. So that's what we're saying, hey, this is how gases behave. Now, look at the picture. And you see the picture indicates a diatomic molecule because there's two of the same size of little balls on there that you draw. And the arrows indicate velocity. And so the arrows, the longer the arrows, the greater the velocity. So if you have to draw any diagrams, the longer the arrows you draw, the greater the velocity you have. Now obviously when they're hitting the sides of the container, remember that collision with the sides of the container is a measure of pressure. The second thing is the total volume of all the gas particles in a system is negligible when compared with the total volume of the system. So that's why we really don't say like, volume of the gas in particular. We say more so volume of the container that it's in. So that's why when we have, when we do mole conversions, 22.4 liters of any type of gas is equivalent to 1 mole, because that's about the size that 1 mole of any gas takes up. But ultimately, we look at the system or the container that it's in for the volume rather than the volume of the gases themselves, because the gases themselves have actually a negligible volume. So for this reason, the ideal gas law assumes that the volume of the gas particles in a system is 0. Now, we know that's not entirely true because we could take the volume of gas systems, but we're going to assume just because it's negligible. It's kind of like the same assumption that we use for mass. The atomic mass is just the mass of the protons and neutrons because the electrons' mass is negligible. So it's kind of like that same concept. The third part, Coulombic forces of attraction or repulsion, and I'm sorry that's spelled wrong there, do not exist between gas particles in a system. So what they're saying is in general, there's really not intermolecular forces between gas particles in a system. So in general, and this is with the kinetic molecular theory, that there are some things against it, of course, but what we're saying is the gases are moving so quickly and they're further enough apart that there's not any intermolecular forces in between the gas molecules. Now, is there in some situations? Yes, and we will discuss that. But in general, there are not. And according to ideal gas law, we're assuming that there's no intermolecular forces. The collisions experienced by gas particles are elastic. So this is number 4. And so I put a little definition down here what elastic really means. And it's a collision where the total kinetic energy of the colliding bodies after collision is equal to the total kinetic energy before collision. So it's kind of like law of conservation of kinetic energy. And we have law of conservation of energy. But elastic collisions can only occur if there's no conversion of kinetic energy into other forms. as like the collision of atoms. So if it's just like hitting the side of something, now if that kinetic energy gets transferred to another atom, then there's still the same amount of kinetic energy total, but not within that particular one. So if you look at the diagram here, we've got kinetic energy. So if a gas hits the wall of a container, then it's going to hit the wall in the same kinetic energy that it leaves the wall. However, let's say you've got here, like what you see on the screen, you got right here. Oops, I'm so sorry, guys. Okay, so you have a fast one, and it's hitting a slower moving particle, and so the kinetic energy is transferred to that. Now, if we're just indicating a slow-moving gas, we use a smaller arrow like you see. And if we're indicating a faster-moving particle, we use a larger arrow. The way that we can determine speed really is how much space they have to move, to be honest. Okay, but bottom line is we have these elastic collisions, and so that's overall. But if we're talking about one particle hitting the wall, same going in, same coming out. And part 5, the average kinetic energy of the gas particles in a system is proportional of the absolute temperature, because kinetic energy, like temperature, literally is a measure of kinetic energy. That's what we're saying here. The gas particles in any system that is kept at the same temperature will have the same average kinetic energy. So the same, when we say average kinetic energy, again, that's the temperature. So like it's possible, think about, I'm just looking outside right now and I'm seeing the wind blow and I know it's cold outside. And so the temperature right now reads like, in the teens. But if you think about it, that's not every particle out there is moving at the same kinetic energy. So overall, there's an average kinetic energy of these air masses and air systems out there, and that's what the temperature shows us, is that's the same average kinetic energy. So if you look at this system here, we've got 250 Kelvin and 250 Kelvin, and even though the systems are different in that we've got a diatomic in system 1, and we have a molecule in system 2 that has 2 different atoms in it. And it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like there's the same number. So it doesn't matter what it is, because again, it's gaseous systems, but it's 250 degrees Kelvin. So notice in system 1, some of the particles are moving fast, some of them are moving slower. In system 2, they all seem to be moving closer to the same speed, but they're the same average kinetic energy. And that's what temperature is. And we've got the kinetic energy of gas molecules, and it's more of a, just a rotation. So translational energy is basically when gas molecules, they move through space in straight lines. When they hit the wall of a container, it's like they spin and they keep moving in straight lines. Now, rotational energy is exactly what it is, where gas molecules just rotate in a fixed spot. And vibrational energy is molecules vibrate, like when we do our whole little solid liquid gas thing, when I stand and I act silly. So vibrational energy is when you're in one spot and there's just some motion. But most of the gas's particles' kinetic energy is the translational energy and the translational velocity, because they're moving in straight lines, they hit a wall, spin, and keep moving. Now, what this shows is the Maxwell distribution and temperature and pressure. And a lot of times, we call it sometimes you'll hear it as the Maxwell distribution, sometimes you'll hear it as the Boltzmann distribution. It's the same concept. But what you're looking at here is the number of particles versus kinetic energy. So underneath the curve is basically like it shows where your particles are moving. So what you're looking at here is with the red curve. So let's look at the red curve that's pointing at 250 Kelvin. What that means is everything under that curve represents particles. And that shows that some of those particles are moving at a kinetic energy of very low, and some of them are moving at a kinetic energy of very high. But the average movement, or the average kinetic energy, correlates with 250 Kelvin. If you look at the curve, the purple curve for 500 Kelvin, some of the particles are not exactly moving very quickly at all. Some of them are moving very fast, but most of them, so the average kinetic energy for those particles is at 500 Kelvin. So what I want you to see here, and what I want you to focus on, it's kind of like a bell curve. Like old school teachers used to want to do a bell curve where they wanted their average to be like a C, where some students would get A's, some students would get F's, but most students got C's. So aren't you kind of glad we don't go on bell curves anymore? Okay, so the average kinetic energy of the particles in a system increases as the temperature increases. So again, kinetic energy and temperature is forever tied together. At any given temperature, the particles with less kinetic energy exert a lower pressure. So that means, think about this, there's less kinetic energy, less motion, less collisions. The particles with more kinetic energy exert a higher pressure. So again, you've got more energy, more motion, more collisions with your container. So the total pressure exerted by the gas is the average. When we go to calculate, so you'll see this calculation on your paper or on your your reference sheet. And this is calculating the kinetic energy of a gas particle. If we were to follow like a single gas particle and see what's going on with that single gas particle, we have to consider its mass and we have to consider the velocity. So if we were to calculate per particle, that kinetic energy is 1/2 times a particle's mass times the velocity in meters per second. So if you take a look at the molar mass and molecular speed at 25 degrees Celsius, for example, because now we want to look at the mass of the particles. So oxygen has 32 AMU, and remember we go back to atomic mass unit when we're talking about one particle, okay? Helium at 4 AMU, atomic mass units. Hydrogen, a diatomic hydrogen, at 2 AMU, atomic mass units. So I want you to see that the molecular speed increases with less mass. Well, that makes sense, okay? You guys can run a lot faster than I can. But I also want you to see the peaks, the relative number of molecules at a given speed. So when you have a higher mass, you're actually going to have your molecular speed, the overall kinetic energy of your molecular speed to create your average is going to be at a smaller zone, just like you see with the peak being a lot higher and the purple lines not covering as much molecular speed. So as the mass decreases, the average velocity increases. That's what we're looking at here. At any given temperature, the average kinetic energy of all gas particles is the same. So again, that's what temperature is the average kinetic energy. Gases with smaller molar masses will have higher velocities. Well, you guys are going to run faster than me. And gases with larger molar masses will have lower average velocities. So again, we go back to this equation. So you guys take it in, rationalize it, reason with it, and memorize the key terms for each of it. But overall, just learn how gases work. And so the way to use kinetic molecular theory is to reference continuously of how ideal gases work. All right, hang in there. Take care. Bye-bye.